Bismillahirrahmanirrahim. Assalamualaikum and a very good morning, guys. Okay. For today, I need to record the note first because I have something to do regarding the accreditation of the labs after this. Alright, guys. First of all, I would like to thank all of you because you have done the assignment using the technique of different thinking hat jigsaw group method. It's very perfect for me. Thank you, guys. You understand well how to how to organize the discussion for the group assignments. Even though we are we are learning through an online approach, but you have done well for that. Thank you. Congratulations. Okay, for today we will continue for the last part of chapter 1, which is about general procedures on solution preparation. Okay. All right. In analytical chemistry, sometimes we need to prepare a series of, for example, concentration. A solution with a different concentrations for what? Especially for first one is for the calibration of the instrument. Right? So concentration is the amount of solute in a known amount of a solution. So what is a concentration? Is amount of solute divided by the amount of solution. Right? And a unit for concentrations, the first one we have molarity, which is the mole of solute divided by the liter of solutions. A second one is molality. What is the difference? Don't be confused because the first one we have molarity and the second one we have molality. So the difference is for molality it is the unit for moles of solute divided by kilogram of solvent, right? The first one molarity is mole of solute divided by a liter of solution, but the second one molality is mole of solute divided by kilogram of solvent. Alright, the third one we have normality. And okay, this is not common. We are not using normality oftenly. Okay, it is a unit that can only be calculated when we deal with a reaction because normality is a function of equivalence, right? And next one we have parts per million, ppm. Okay, what is parts per million? It is milligram of solute divided by a liter of solution. Okay, and then we have also a common one, okay, parts per billion, ppb. Okay, it is a microgram of solute divided by a liter of solutions. And then we have a percentage of concentration in term of a percentage. We call it percent concentration. For the first one, for example, we have percentage of weight by weight. We call it weight by weight because the weight of solute divided by the weight of solution. All right, and then we have percent of weight by volume, and then we have percentage of volume by volume. All right. All right. So here we have molarity, number of moles of solute divided by liters of solution. Okay, it's concentration for a particular chemical species, meaning that molarity can be a molarity of, for example, we have calcium nitrate. Okay, in we dissolve calcium nitrate. So for example, we have 1 mole of calcium nitrate dissolved in 1 liter of solution. So we have 1 molar of calcium nitrate. But for molarity, we can have the molarity for a different species in the solution. For example, if we dissolve calcium nitrate in a solution, we have calcium ion as well as the nitrate ion. So we can have the molarity of calcium ion and we can have the molarity of the nitrate ion. So now when we dissolve calcium nitrate, so we have 1 mole of calcium ion and we have 2 mole. Now we have 2 mole of nitrate ion because in stoichiometric we have to form 1 mole of calcium nitrate we need to have 2 mole of nitrate combining with 1 mole of calcium. Because the chemical formula is Ca, okay, and then in the bracket NO3 2, okay, and then we have molarity, okay, this number of mole of solute divided by kilogram of solution, and then we have formality, number mole of solute divided by liters of solution. So what is the difference between molarity and formality? Okay, for formality we doesn't use it for a different or single kind of ion. It is a total concentration of a total substance total concentration without regard to its specific chemical form. We don't use formality for any ion because it is old school for formality. Normally we use molarity for differentiate the concentration of a single ion. Okay, don't worry. Okay, most of the concentration unit we only use molarity, right? Okay, and now for example, what is the molarity of a salt solution when 0.6 gram sodium chloride was dissolved in 100 ml of water? So now molarity is the mole divided by liter. We have 0.6 gram, okay, so times, okay, mole divided by 1 mole divided by 58.5 gram times, okay, 1 divided by 0.1 liter, right? So why? Okay, because the molecular weight of sodium chloride is 58.5 gram per mole. Okay, so we need to times the weight. Okay, so we get the number of mole of the sodium chloride, and then we divide by the volume of the water. We have 100 ml, so we have 0.1 mole per liter, or 0.1 molar. We call it 0.1 molar, right? Okay, now concentration in terms of percent composition. Okay, right, the concentration of substance in commercial aqueous reagent, organic solvents, and commercial household products are usually expressed in percent composition. Okay, we normally have our shampoo, our soaps, or any commercial pharmaceutical product, okay, that in the form of aqueous. Okay, normally they are using weight percentage, all right, or volume percentage, okay, to express their concentration. For example, weight percent, okay, they remember the weight of solute divided by weight of solution and times 100. For volume percent, okay, it's the volume of solute divided by volume of solution times 100%, right? And then a percentage of weak volume, it is weak of solute divided by volume of solution times 100%, right? For example, we have 37% label on the hydrochloric acid reagent bottle, meaning that, okay, it is 37 what? 37. If we want to use percentage weight by weight, it is 37 gram divided by 37 gram of hydrochloric acid divided by 100 gram of solution. So we have 37% of hydrochloric acid, right? So what about the salicylic acid shampoo? 6% weight by weight. So it is 6% of salicylic acid, okay, in a, okay, it is 6 gram salicylic acid in 100 gram of the solution of the shampoo, right? Okay. That okay, I told you. Okay. All right. Okay, this one. 0.05%, okay, of epinestine HCl ophthalmic solution. Okay, so what is the weight per volume percent? Okay, remember, weight per volume percent is weight of solute divided by a total volume of solution times 100, and then we have example, what is the weak percent of a solution of 0.05 gram epinastine in 100 ml of solution? So 0.05 gram, okay, divided by 100 times 100. So we have 0.05% weight by volume. Right. So this is 33% hydrochloric acid, meaning that we have, if this is weight by weight percentage, we have 33 gram of hydrochloric acid in 100 gram of the solution, the aqueous solution. Right. So volume per volume percent. Okay, for example, the acid is in volume per volume percent. Okay, so it is a volume of solute divided by volume of solution times 100. So how many milliliter of hydrochloric acid needs to be added into 100 ml of solution to prepare 33% of volume by volume hydrochloric acid? So we have, so the answer is we have to put 33 ml of hydrochloric acid. Right? Okay, let's see the photo. Okay. If someone, okay, feels bleeding, okay, inside maybe an open sea, okay, so the shark can smell, okay, the blood from very far. Okay, that is the special of the shark. Okay, some shark can detect odors, mostly blood, at concentration of 1 part per billion. All right, wow, that's very, the shark is very sensitive in their sense of blood detection. Okay, so now just how small is a part per million or part per billion? Remember, in one Olympic size of swimming pool, okay, we have 660,000 gallons of water. So 1 ppm of a soda in, just to imagine, okay, 1 ppm of soda is equal to 1 and a quarter 2 little bottles of soda, okay, inside an Olympic size of swimming pool. So that is 1 ppm. So what about 1 ppb, 1 part per billion? It is a half teaspoon of a soda inside an Olympic size of swimming pool, right? Okay, so 1 million, 1 billion, and 1 trillion. Okay, we represent all of this in terms of 10 to the power of 6, 10 to the power of 9, and 10 to the power of 12, right? So 1 part per million is 1 in 10 to the power of 6, right? So 1 part per billion is 1 in 10 to the power of 9, and 1 part per billion is 1 in 10 to the power of 12. That is the unit, basic unit. Okay. So what about 1 part per million, 1 ppm? So 1 unit volume in a million unit volume. For example, blood in ocean. Okay. So 1 unit mass in million unit mass. So mineral in solid. That is example. So 1 unit mass in million unit of volume. That is salt in water. All right. So the commonly used unit for ppm, okay, for the concentration is ppm. 1 unit mass in a million unit mass, okay, mineral in solid, it is ppm, grams of solute, okay, divided by gram of the solid. Okay, so therefore the unit will be microgram per gram. How it become microgram per gram? Okay, just divide the unit. All right. Also, we can convert it to milligram per kilogram. So 1 ppm is microgram divided by gram, okay, or milligram divided by kilogram. This is the basic unit, you just convert. Okay, as an example, a 2.6 gram sample of plant tissue was analyzed and found to contain 3.6 microgram zinc. So what is the concentration of zinc in the plant? Okay, in ppm. So we have the solute and we have the the total volume, the total weight. Okay, so 3.6 microgram divided by 2.6 gram. So we have 1.4 microgram per gram or ppm, right? Okay, for example, 1 unit mass in a million unit volume. Okay, salt in water. Remember, for water we just assume that 1 gram is equivalent to 1 milliliter and 1 kilogram is equivalent to 1 liter. Okay, despite the density of the water. Right, so 1 ppm is gram of solute in gram divided by volume of the total water, right? So we have microgram per milliliter or milligram per liter. Commonly we use milligram per liter, right? Okay, this is for example. Okay, ceramide 2000, they put ceramide 2000 star, okay, and then cream. Okay, a 0.25 milliliter serum sample was analyzed for glucose content and found to contain 26.7 microgram. Calculate the concentration of glucose in ppm. So therefore, 1 ppm is equal to 1 microgram per gram, can also converted to 1 microgram per milliliter or 1 microgram per liter. Alright. So for trace analysis in liquid samples, it is analysis of very little amount of analytes. Okay, parts per billion is gram of solute divided by 1 billion gram of solution. Therefore, 1 ppb is equal to 1 nanogram of solute divided by 1 gram of solution, or 1 nanogram of solute divided by 1 milliliter of solution, or 1 microgram of solute divided by 1 liter of solution. So commonly we use 1 microgram per liter to represent part per billion. What about parts per trillion? Okay, also ppt. Okay, this is not commonly used. Okay, normally we are using ppm and ppb, right? So what about parts per trillion? Is 1 gram of solute divided by 1 trillion of a gram of solution. Therefore, 1 ppt, 1 part per trillion, is equal to 1 picogram of solute divided by 1 gram of solution, and equal to 1 picogram of solute divided by 1 milliliter of solution, or 1 nanogram of solute divided by 1 liter of solution. It is not commonly used, but you need to know about it. Okay, so converting percent composition to molar concentration. Okay, converting a commercial term to easier laboratory term. Okay, so percent composition is a term that commercially used for all the products that involving the concentration. Okay, that they need to declare the concentration. So we need to convert it into an easier laboratory term, because in the lab, okay, we commonly use other term instead of the commercial term. For example, a commercial aqueous ammonia bottle is labeled as 28% week by week and has a density of 0.899 gram per milliliter and molecular weight of 17.03 gram per mole. Let's say you want to convert the concentration into molarity for easier calculation in your lab book. How can you do that? Okay, so the first one, okay, the weak percentage, 28%, right? So 28 gram of solute divided by 100 gram of solution times the density. We need to time the density first, because the density is given there, right? So we have 0.2517 gram per mil of the ammonia. Okay, and then we need to divide by the molecular weight, so that we have the amount of mole. Okay, how many mole? So we have 0.01478 mole per milliliter times 1000 milliliter per 1 liter to convert it into molarity. So we have 14.8 molar, or we call the molarity as molar unit. So we have 14.8 mol per liter, or 14.8 molar. Okay, so how to prepare a solution? Okay, for example, how to prepare 250 ml of 0.1 molar sodium hydroxide from sodium hydroxide solid. Okay, given that the sodium hydroxide, the molecular weight is 40 gram per mole. Okay, the first one, you need to calculate the weight of the sodium hydroxide pellet using molecular weight to produce 0.1 molar. So calculate it, right? And then you weigh it. Okay, after you calculate, you have exactly how many gram of the sodium hydroxide you need to take, and then generally plus minus 0.1 milligram, okay, and up to 4 decimal place in gram. Okay, we just weigh it, the pellet. Okay, and then you dissolve the sodium hydroxide pellet in a water. Okay, quantitatively with rinsing. You need to clear all the sodium hydroxide in your container, and then you put it in the volumetric flask and dilute to the mark. So we have prepared the 250 ml of 0.1 molar of sodium hydroxide. Okay, preparation of solution. Example, how to prepare 25 ml of 0.01 molar glutamic acid solution from glutamic acid powder, given that a molecular weight of glutamic acid is 147.13 gram per mole of the glutamic acid. Alright, this one you need to do by your own individually. Okay, calculate it, prepare solution. You just referring to the example, you just mention how to prepare the solution of glutamic acid. And after that, we have dilution of solution. Okay, are you familiar with this? M1V1, M2V2. Okay, the mole of solute in concentrated, okay, one solution equal to the mole in dilute 2 solution. Okay, so M1, okay, is initial concentration of solution. V1 is volume of concentrated solution transferred. M2 is concentration of final solution that is diluted, and V2 is volume of final standard solution. For example, describe the preparation, okay, of 50 ml of 0.1 molar sodium hydroxide solution from 0.5 molar solution. Okay, are you familiar with this dilution? Okay, we need to calculate, okay, and then how to prepare it. Okay, we need the glassware equipment and on the dilution process, and then we need to have the specific volumetric flask and so on, so that we can prepare the diluted solution. Okay, let's see, we have, for example, okay, what is the volume needed to prepare 2.5 liter of 0.6 molar sulfuric acid, starting with the concentrated acid that is 18 molar. Okay, so we have M1V1, M2V2. What is the initial concentration that we need to prepare? 18 molar. So M1 is 18 molar. So how much is the volume that we need to take to prepare what 0.36 molar? So we don't know, we need to calculate it first. So what is the final concentration that we want is 0.36 molar. What is the final volume we need is 2.5 liter. So we can calculate the volume now because we have all the other value. Okay, so guys, so for the preparation of laboratory sample, okay, so we need a pre-treatment method. Okay, what is a pre-treatment method? The objective is converting the sample to a useful form. How? The solids are usually ground to a suitable particulate size to get a homogeneous sample, and then dry the sample to get rid of the absorption water. Okay, we need to remove the moisture first. Okay, we need to dry the sample. Okay, okay, the solid, we need to dry the solid first, okay, up to 110 to 120 degrees Celsius for 1 hour, and cool it in desiccator before weighing. All right, so for prepare the solution, okay, of the sample, okay, most analysts Okay, most analyses are performed on solutions. A solvent is chosen that dissolves the whole sample without decomposing the analyte. Okay, for example, this is how to prepare, okay, a laboratory sample. Okay, so the pre-treatment is we need to dry it, remove the moisture. Okay, we need to dry it first again, and then we after that we need to choose a solvent that can dissolve our sample, okay, without decomposing the analyte. So several sources of error are encountered in the sample dissolution step. The first one is incomplete dissolution of the analyte, losses of the analyte by the volatilization and introduction of analyte as a solvent contamination, and then contamination from the reaction of the solvent with a vessel wall and so on. Okay, so and after that to reduce the error, we need to replicate the sample. Okay, we need to do more than one. For example, normally we use 3 replicate. Okay, a portion of material of approximately the same size that is carried, okay, for the procedure at the same time and the same way. And then we need to always perform unless the quantity of the analyte as pen or other. Okay, so this is on how to prepare a laboratory sample. Okay, we need to the first step is we need to pre-treatment. Okay, and then we prepare, and then we have to need the replicate. Okay, that's all for chapter 1. Okay, we have learned all the subtopics in chapter 1, so hopefully you are ready to to learn the next chapter. Okay, and then for this chapter I will do I will give a simple quiz for you. Okay, just to the quiz is counted in the marks. Okay, don't worry. Okay, it's not so difficult. Okay, just to what you have to do is just read all the notes. Okay, by that, goodbye and assalamualaikum.